Welcome to this session on Total ROP Enhancing Techniques and Technologies, sub-module 1 of 4. In this module, we'll focus on how to monitor well performance in real time, use drill-off curves, and apply efficiency metrics like mechanical specific energy and bit friction. Let's begin by outlining today's learning objectives. In this sub-module, we will focus on 5 key objectives. First, we'll understand drill-off curve regions and identify the sources of inefficiency that can limit performance. Second, we'll look at how dysfunctions such as balling, poor hole cleaning, or vibrations can restrict rate of penetration. Third, we'll apply 2 important concepts, mechanical specific energy and the bit friction coefficient, to evaluate drilling efficiency in real time. Fourth, we'll examine how drill-off tests can be used to optimize weight on bit and rotary speed for maximum rate of penetration. Finally, we'll see how to recognize bit wear impacts using MSE trends and friction analysis, which provide a powerful way to detect declining bit condition before it becomes critical. With these objectives in mind, let's move into the technical content, starting with on-bottom ROP enhancement. When we talk about enhancing rate of penetration while on bottom, we need to understand the balance between input energy and output performance. At surface, we supply energy through weight on bit and rotary speed, but only part of that energy is effectively transferred to the bit face. Along the way, frictional losses in the wellbore consume part of the input, particularly in deviated or extended reach wells where string contact is higher. In addition, downhole dynamics such as shocks and vibrations can dissipate a significant portion of the applied energy, leaving less available for efficient rock cutting. Let's look at the concept of input versus output energy in drilling. At the surface, we apply energy primarily through 2 parameters, weight on bit and rotary speed. These forces are transmitted downhole along the drill string, but not all of that energy reaches the bit face. A portion is lost to friction against the wellbore walls, especially in deviated or horizontal wells. Other losses occur due to shocks, stick slip, whirl, and axial or torsional vibrations, all of which waste energy that should be going into cutting rock. In the diagram, energy is input at the top, followed by 2 main pathways of loss, friction losses and shock vibration energy dissipation. What remains is the effective energy at the bit. This net energy is what controls the rate of penetration. The key point here is that energy efficiency, not just energy input, drives drilling performance. 2 wells with the same applied surface parameters can drill very differently depending on how efficiently that energy is delivered to the bit. With this context, let's examine how drill-off curves historically evolved to help us visualize and quantify these efficiency losses. The traditional drill-off curve was first defined through experimentation in the 1950s. At that time, dysfunction was mainly through bit balling. The original concept was simple: apply incremental weight on bit and measure the corresponding rate of penetration to establish a relationship. Over time, our understanding has grown. Today, dysfunction is more likely to be encountered through downhole vibrations and shocks rather than deliberate bit balling. Additionally, the widespread use of non-aqueous fluids has altered drilling dynamics compared with early water-based systems. The drill-off curve remains a valuable diagnostic tool because it reveals how much of the energy we apply is actually producing depth of cut versus being lost to dysfunction. The curve illustrates the relationship between weight on bit and ROP. Theoretical expectations show a steady upward trend, but deviations occur once founder, balling, or vibration limits are reached. This is where the curve flattens or falls short of expectations. By addressing the causes of dysfunction, the flounder point can be raised, increasing the ROP. So, the drill-off curve provides both a benchmark and a diagnostic tool. Next, we'll connect specific regions of the curve to the types of inefficiency they represent. Here we break the drill-off curve into 3 distinct regions, each associated with different types of inefficiency. In region 1, we see inadequate weight on bit being applied. Here, the bit cannot achieve the necessary depth of cut, and penetration is slow simply because the tool is underloaded. The inefficiency is bit-related rather than caused by external dysfunctions. Region 2 is where penetration is limited by non-bit factors. These include directional control requirements, hole cleaning limitations, shaker capacity constraints, or the available weight in the bottom hole assembly. In this region, the bit may be capable of cutting faster, but external conditions prevent it from doing so. Region 3 occurs when founder and dysfunction dominate. This is where we see balling, stick slip, whirl, or severe vibrations limiting ROP, regardless of how much additional weight is applied. The theoretical relationship, if founder were not present, would continue upward, but in practice the curve flattens. On the graph shows weight on bit is plotted against ROP. You'll see the 3 labelled regions with causes of inefficiency listed alongside. With these regions defined, we can now relate the curve back to theoretical expectations and discuss how to identify founder in practice. Now let's focus on founder identification. In theory, weight on bit and rate of penetration should follow a predictable relationship. More weight leads to a deeper cut and therefore a higher penetration rate. However, in practice, we often see variation from this expected curve. These deviations point to dysfunction. Bit founder can occur for several reasons. Bit balling, where cuttings accumulate around the cutters, reduces cutting efficiency. Bottom hole balling, where cuttings clog the hole below the bit, creates a similar effect. Vibrations from stick slip also limit the bit's ability to cut effectively. The net result is a failure to achieve the expected depth of cut. On the chart, you can see the idealized weight on bit ROP curve alongside notional depictions of dysfunction. The illustrations highlight conditions such as stick slip, whirl, and balling. Each of these represents a mechanism where added weight fails to translate into improved penetration. The main lesson here is that variation from theory is not random. It's a signal of dysfunction. Identifying these departures early allows corrective action before performance is severely impacted. With this in mind, let's now explore the relationship between ROP and torque. Rate of penetration and torque are intimately linked because both are governed by how effectively the bit engages the formation. As weight on bit is increased, the bit cuts more aggressively and torque rises in proportion. This relationship allows us to use torque as an indicator of drilling efficiency. When the expected torque increase does not occur alongside greater penetration, it suggests that the bit is no longer cutting effectively, perhaps due to balling, poor cleaning, or vibration. Conversely, sudden spikes in torque without a corresponding increase in ROP may indicate founder, excessive friction, or dysfunction. The chart shows torque and penetration trends should move together under normal conditions. Any departure between the two is diagnostic. This is why torque measurement, in conjunction with penetration rate, is such a powerful real-time tool for identifying problems. In practice, monitoring both variables together helps confirm whether poor ROP is due to insufficient bit aggressiveness, surface parameter limits, or downhole dysfunction. This brings us directly to the concept of bit friction coefficient, which quantifies aggressiveness in numerical terms. The bit friction coefficient, symbolized by the Greek letter mu, provides a way to quantify the aggressiveness of the bit. It is defined by the relationship between torque and weight on bit. Mathematically, it is expressed as mu equals 36 times torque, divided by the product of bit diameter and weight on bit. In simpler terms, mu tells us how much torque is being generated for a given bit load. A higher mu means the bit is cutting more aggressively into the formation, while a lower mu suggests the bit is sliding or scraping without effective cutting. Each bit type has typical M ranges. For example, steel tooth roller cones usually range between 0.15 and 0.26, carbide tooth cones between 0.12 and 0.24, 0.26, impregnated bits around 0.3 to 0.6, and PDC bits can be as high as 2.0. TOR represents torque in foot-pounds, weight on bit is weight on bit in pounds, and D is bit diameter in inches. The constant 36 simply converts units. Understanding mu is valuable because it gives us a real-time measure of how the bit is interacting with the rock. Deviations from expected values can signal wear, balling, or changing formation properties. Next, we'll see how mu can be calculated dynamically in real time using downhole measurements. Calculating mu in real time allows us to use it as a diagnostic tool rather than just a static measurement. To be accurate, we need to rely on downhole values of torque and weight rather than surface estimates. This ensures that frictional effects and losses along the drill string are accounted for. Once we have downhole torque and weight, we can calculate mu continuously while drilling. Changes in mu directly reflect changes in the relationship between weight and torque. A sudden rise may indicate founder, bit balling, or increased aggressiveness, while a drop might suggest dulling or reduced engagement. This calculation becomes even more powerful when we compare mu with other measurements, such as mechanical specific energy, or MSE, and mechanical efficiency. Together, these metrics provide a complete picture of how efficiently the bit is cutting rock. The log shows mu calculated from the surface in blue and mu calculated downhole in red. What it shows is the loss of energy along the string. The divergence is indicating wear, and the downhole calculated measurement is declining. Now that we've introduced real-time mu, let's move to drill-off testing, which is one of the most practical methods for optimizing parameters. Drill-off tests are one of the most practical tools we have for optimizing drilling parameters. The purpose of these tests is straightforward: to determine the maximum rate of penetration achievable for a given weight on bit, and then to identify the best rotary speed at that weight. The procedure begins by applying a specific weight on bit, then measuring the time and depth required for the bit to drill off a set load, commonly 10,000 pounds. By repeating this process at different weights, we can identify the point where ROP is maximized. Once this optimal weight is determined, we then vary rotary speed, measuring the time taken to drill a standard length, often 1 foot, to find the RPM that delivers the fastest progress. The cross plots are used to test weight on bit and RPM against time and against ROP. The optimum is highlighted as delivering the highest ROP. This sets the stage for understanding the mechanical specific energy equation, which formalizes the relationship between torque, weight, penetration, and energy. Mechanical specific energy, or MSE, is a powerful concept that quantifies the energy required to remove a unit volume of rock. It combines the effects of torque, rotary speed, weight on bit, hole diameter, and penetration rate into a single metric. The equation shown is MSE equals 480 times torque times RPM divided by hole diameter squared times ROP plus 4 times weight 1 bit divided by pi times hole diameter squared. In plain language, the first term represents the rotational energy input, while the second term accounts for the axial or depth of cut energy component. Together, they capture the total energy expended to drill the rock. The units are expressed in pounds per square inch, allowing direct comparison to formation strength. When MSE is close to rock strength, drilling is efficient. When it is much higher, energy is being wasted, usually due to dysfunction, poor cleaning, or dull bits. With the formula in mind, we can now discuss bit efficiency, why no bit ever reaches 100%, and how we adjust MSE accordingly. Mechanical efficiency, expressed here as EFFM, is a way to adjust MSE to reflect real-world bit performance. The formula is EFFM equals MSE minimum divided by MSE multiplied by 100. In other words, we compare the lowest achievable MSE with the measured value to calculate efficiency as a percentage. Originally, it was believed that MSE minimum would be roughly equal to rock strength. In practice, however, testing has shown that bits are far less efficient. For MSE purposes, Bits are typically only 25 to 45% efficient. This variation depends on drilling conditions, bit type, and whether we are using surface or downhole data. The key point is that MSE calculations must be corrected for bit efficiency to give meaningful results. Without adjustment, we would consistently overestimate how much energy is actually required to cut the rock. Recognizing this limitation allows us to use MSE as a comparative tool rather than an absolute measure. With bit efficiency in place, we can now combine MSE and the bit friction coefficient to better understand drilling aggressiveness and performance. Adjusted mechanical specific energy refines the standard MSE calculation by factoring in hydraulic conditions. The idea is that bit performance is not governed by mechanical forces alone. The efficiency of cuttings removal and hydraulic cleaning also plays a critical role in sustaining penetration rates. When hole cleaning is poor or nozzle hydraulics are insufficient, MSE will appear higher than expected. This is because additional energy is being wasted regrinding cuttings rather than cutting fresh rock. By adjusting MSE for hydraulic effects, we get a more accurate measure of true efficiency. The chart referenced here comes from SPE work by Fred Dupriest and William Koderitz, showing how real-time MSE surveillance links drilling efficiency to both mechanical and hydraulic parameters. The key point is that operators can use MSE adjusted to fine-tune pump rates, nozzle selection, and flow regimes. By integrating hydraulics into MSE monitoring, we gain a complete view of downhole efficiency. This bridges the gap between bit mechanics and fluid dynamics. On the next slide, we'll look at examples where MSE reveals potential bit wear. Here we illustrate how MSE trends can help us detect potential bit wear. As a bit dulls, its cutting structure becomes less aggressive, requiring more energy to achieve the same depth of cut. This manifests as a rising MSE value over time, even when weight on bit and RPM remain constant. In the examples shown, increasing MSE correlates with observed dulling on retrieved bits. The relationship is not perfect, but consistent patterns make it a valuable surveillance tool. A new bit typically drills at lower MSE values, while a worn bit shows progressively higher readings for equivalent parameters. The practical application is straightforward. By monitoring MSE continuously, we can project when a bit change will be required. This prevents excessive wear, reduces wasted rig time, and allows for better bit life management. The graphs on this slide highlight real data where MSE increases flagged bit dulling well before catastrophic failure. This kind of early warning is essential in high-cost environments where unscheduled trips are expensive. Next, we'll extend the theme of surveillance into hazard avoidance, showing how monitoring provides more context for better decisions. Hazard avoidance is another benefit of real-time monitoring and analysis. By integrating data such as depth of cut, torque, and sonic-derived UCS logs, we can place drilling performance in geological context. This allows us to recognize potential risks earlier and make informed adjustments. The DOC/DTCO log example shown here comes from dipole sonic data used to calculate unconfined compressive strength. By comparing this strength with measured drilling responses, we can spot anomalies that may indicate higher risk of dysfunction, stuck pipe, or even well control issues. The principle is that more context leads to better decisions. Surveillance provides the additional information needed to assess whether drilling parameters are appropriate for the formation being drilled. Instead of reacting to problems after they occur, we proactively adjust to prevent incidents. This theme of proactive monitoring ties directly into the next slide, where we'll examine how MSE trends also relate to bit wear management and projection. Here, we demonstrate how mechanical specific energy can be utilized to dynamically estimate bit wear. The principle is that friction increases as a bit becomes dull, and this is reflected in rising MSE values during both drilling on and drilling off. By trending MSE against time and depth, we can project how much useful life remains in the bit. On the left, the chart compares ROP projections with the same bit versus those with a new bit. The last curve on the log is the computed bit wear. This tends up significantly at the end, which demonstrates higher energy demand for lower penetration. On the right, MSE values are cross-checked with bit friction coefficient, providing further confirmation of wear, but this time the confirmation leads to a decision to change the bit. The advantage of this method is that it allows us to make informed trip decisions rather than reactive ones. Instead of waiting until penetration collapses, we can forecast bit replacement at an optimal point. This minimizes wasted drilling energy, reduces non-productive time, and extends tool life overall. In summary, monitoring MSE alongside MU is a practical and real-time method for estimating bit wear. With this technical content covered, we can now review the learning objectives of the module and reflect on how each has been achieved. Let's take a moment to review the objectives we set out at the beginning of this submodule. First, we aim to understand drill-off curve regions and the inefficiency causes behind them. We explored how regions 1, 2, and 3 represent underloading, operational limits, and dysfunction, respectively. Second, we set out to identify ROP limitations caused by dysfunction, balling, and vibrations. We saw how deviations from theoretical weight on bit ROP curves point directly to founder mechanisms such as stick-slip, whirl, or balling. Third, we applied mechanical specific energy and the bit friction coefficient, MU, to measure drilling efficiency in real time. These metrics give us clear, quantitative tools to diagnose problems early. Fourth, we reviewed how drill-off tests can optimize weight on bit and rotary speed to maximize penetration. Finally, we examined how MSE and MU trends reveal bit wear, helping us plan trips more effectively and avoid unnecessary downtime. Each of these objectives has been addressed through practical examples and clear diagnostic methods. This gives us a strong framework for real-time well monitoring and drilling optimization. That concludes submodule 1 of 4 on Total ROP enhancing techniques and technologies. We've covered the fundamentals of drill-off curves, MSE, MU, and their application to drilling performance and bit wear management. Please proceed to the quiz to test your understanding of the concepts discussed. Thank you for your time and attention, and I look forward to our next session.